Imagine looking at time through an ever stronger magnifying glass. We start from one ordinary second, and then we go deeper and deeper. Milliseconds, microseconds, picoseconds, all the way down to the absurdly short Planck time, where our physics starts to fall apart. On the way, we'll see what really happens on these scales, and we'll discover that the second itself is actually a bit artificial, invented by humans, inconvenient for equations, and the truly natural time looks completely different. 1 second, our home unit. Let's begin with that 1 second, which feels so calm to us. In 1 second, light travels almost 300,000 kilometers. That's enough to go around the Earth about 7.5 times, reach the Moon in about 1.3 seconds. In that same second, the Earth moves about 30 kilometers along its orbit. The International Space Station flies approximately 7.7 kilometers. About 4 million cells in your body are born and die. And the Sun turns 4 million tons of mass into energy every second, nonstop. Through every square centimeter of your skin, around 60 billion neutrinos from the Sun pass each second. You don't glow, you don't buzz, you don't feel anything. These particles are so non-interacting that practically the entire universe is transparent to them. That's 1 second. It looks boring until we peek under the hood. Millisecond, the world of fast reactions. Now we divide time by 1,000. A millisecond is 1,000th of a second. Light travels 300 kilometers in that time. A human blink lasts on average about 200 milliseconds. That's already quite a long epoch in the world of milliseconds. But in nature, there are creatures for which that amount of time is an eternity. The mantis shrimp punches with its fist in about 2 milliseconds. It does it so violently that the water locally boils. Cavitation bubbles appear. There's a flash and temperatures of thousands of degrees, a miniature thermal bomb in a claw. Some mosquitoes can flap their wings almost 1,000 times per second, which means one flap within a millisecond. For them, air is like jelly they whip continuously. In the plant world, the carnivorous bladderwort snaps open its underwater trap in about 2 milliseconds, creating an almost vacuum and sucking in the prey before it even realizes it has a problem. Our consciousness also works in milliseconds. The brain needs about 80 milliseconds to process sensory signals and stitch them into a single impression of now. So we always live slightly in the past. This window of a few dozen milliseconds acts as an editing buffer. The brain matches events, shifts them slightly in time so they appear synchronized. Technology? An airbag in a car deploys in about 50 milliseconds. Graphics cards can render frames faster than 1 millisecond, but our brain still can't squeeze infinite smoothness out of that. Microsecond, a millionth of a second. We divide by 1,000 again. Microsecond, light travels 300 meters, a bullet barely a millimeter on these time scales. A crack in glass propagates at about that speed in microseconds. In inkjet printers, a heating element boils a tiny droplet of ink in a few microseconds, and in the next tens of microseconds, ejects it from the nozzle at enormous speed. Ants of the species Mystrium camilla snap their jaws in about 20 microseconds, reaching up to 90 meters per second, a record-breaking movement in the animal world. On the molecular level, microseconds are everyday life. Proteins can fold into their active structure in about that time after being synthesized. Ion channels in cell membranes open and close in microseconds. Our auditory system can detect a difference in arrival time of sound between the left and right ear on the order of 10 microseconds. That's enough to determine the direction from which someone is calling us. Nanosecond and picosecond, the world of electronics and reactions. Nanosecond, a billionth of a second. Light travels only 30 centimeters in that time. The chain reaction in an atomic bomb lasts hundreds of nanoseconds. The thermonuclear reaction in a hydrogen bomb, about 20 nanoseconds. The LHC Hadron Collider makes proton bunches collide every 25 nanoseconds, 40 million times per second. Atomic clocks in GPS satellites must measure time with nanosecond accuracy. Otherwise, the position would be off by tens of centimeters. We go even lower. Picosecond, a trillionth of a second. Light travels 3 millimeters in that time. For comparison, a second relates to a picosecond, roughly like a second relates to 32,000 years. In picoseconds, a typical hydrogen bond between water molecules lives around 1 picosecond. In 1 second, such a bond can break and reform 1 trillion times. Spontaneous processes in solutions, for example, an electron being captured by a water molecule, typically happen in about a picosecond. The reshaping of electron clouds during chemical reactions, the thing we draw in school as curly arrows showing bond shifts, in reality happens on the picosecond scale. The CPUs in our computers work at frequencies of a few gigahertz. 4 gigahertz means a clock cycle every 0.25 nanoseconds, that is 250 picoseconds. In that time, light travels a few centimeters and the CPU does another tick, 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 billions of times per second. Femtosecond, chemistry in slow motion. Femtosecond, a quadrillionth of a second. Light travels 300 nanometers in that time, less than the size of a bacterium. That's a characteristic timescale for vibrations of chemical bonds, the first stages of chemical reactions, the breathing of molecules, stretching, twisting, rotating. There is an entire field, femtochemistry, devoted to studying chemical reactions precisely on these timescales. Femtosecond lasers generate ultra-short flashes of light that can be used like a strobe to illuminate successive phases of a reaction. Thanks to this, we know, for example, that in the molecule responsible for vision in the retina, the change of shape after absorbing a photon happens in about 200 femtoseconds. That's one of the most basic steps in the process of seeing, pushed by evolution almost to the physical speed limit. Attosecond, the motion of electrons, a quintillionth of a second. Light travels only 3 nanometers in that time, roughly the size of a few atoms in a row. This is the scale of electron motion in atoms and molecules, quantum tunneling, the subtlest charge rearrangements. If we imagine an electron orbiting the nucleus in a classical orbit, which is not correct but it's intuitive, then one such year would last tens of attoseconds. Attosecond lasers now allow us to track electron motion in real time, study delays in photoemission, observe how charge shifts in a molecule after a photon is absorbed. The famous triple alpha process in stars, which produces carbon, also plays out in attoseconds. The intermediate beryllium-8 nucleus lives for about tens of attoseconds. That's how long it has to capture a third helium nucleus and form carbon-12 before it decays. If this process were even a bit slower, the amount of carbon in the universe would be dramatically smaller. And without carbon, there would be neither us nor this story. Zeptosecond, yoctosecond, rontosecond, the extreme. Zeptosecond, a sextillionth of a second. Light travels 300 femtometers, then, roughly the size of an atomic nucleus. On these timescales, atomic nuclei drop from excited states to lower ones, emitting gamma photons. For example, the time it takes a photon to pass through an H2 molecule has been measured to be on the order of hundreds of zeptoseconds. Yoctosecond, another factor of 1,000 shorter. Light travels 3 femtometers, less than the diameter of a proton. Some extremely short-lived isotopes and very heavy particles, like the Higgs boson, live this long. They are born and decay in yoctoseconds, leaving only a trace in detectors. Rontosecond, another step down. Light travels about 3 attometers during a rontosecond. That's a distance comparable to the size we attribute to some of the simplest point-like objects in physical models. On this timescale, the W and Z bosons, carriers of the weak interaction, live only about hundreds of rontoseconds. That's why the weak force acts over such extremely short distances. Its carriers disappear almost instantly. At these levels, time itself seems almost ground into dust. We can go still lower, but there we run into something special, and that is Planck time, the boundary of meaning. So far, we've been happily dividing the second by 1,000 over and over: milliseconds, microseconds, nanoseconds, picoseconds, femtoseconds, attoseconds, down to rontoseconds. But the second itself is conventional. It's not built into nature. Once, it was just 1 divided by 86,400 of an Earth day. Today, it's defined by what happens in a cesium-133 atom. Its official definition is the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between 2 very specific energy levels in the cesium-133 atom. It sounds complicated, but the idea is simple. We take an atomic process that always happens the same way, and we tie our unit of time to it. That's convenient for building clocks, but arbitrary from the universe's perspective. We can do something smarter: build a system of units that isn't based on human conventions, but on fundamental constants themselves. So we take the speed of light, c, the gravitational constant, g, the reduced Planck constant, h, and other constants like Boltzmann's constant, kb, and combine them in such a way that we get a unit of length, the Planck length, a unit of time, the Planck time, a unit of mass, the Planck mass, a unit of temperature, the Planck temperature. In this system, these constants simply have the value 1. They disappear from the equations, and only pure relationships between quantities remain. Planck time is just such a natural time. The interval in which light travels 1 Planck length, the minimal distance that can sensibly be defined before everything collapses into a black hole. Numerically, it's about 10 to the power of negative 44 seconds. But that's already converted into our human second. In the language of the universe, it's simply time equals 1. The key point is, below the Planck time, our current physics stops working. Any device trying to measure shorter intervals would need such enormous energy density that it would collapse into a black hole. So we say that the Planck time is the smallest meaningful interval of time, not because for sure nothing exists beyond it, but because we no longer know how to describe it sensibly. What next? Are time and space really chopped up into Planck pixels? tiny volumetric pixels of space and minimal ticks of time? We don't know. In some theories, like loop quantum gravity, space and time really are quantized in such units. In others, like string theory, time and space remain continuous, but the fundamental objects, vibrating strings, have sizes and frequencies close to Planck scales. For now, Planck time is a boundary for us. Below it, there is a fog of guesses and equations that don't yet fit together. But even without going into that fog, one thing is clear. The second your watch is ticking, the milliseconds in which you blink, the picoseconds in which water molecules vibrate, the attoseconds in which carbon was forged in stars are just different levels of one vast dynamic puzzle. And Planck time is the thin line at the bottom of that scale, beyond which our current description of the world says, I don't know how to go further. And that's exactly what makes this smallest unit of time so fascinating.